what I want to do first is just go over how things are graded so you don't have to stop by my office, and we'll go over the exam. So first problem, it's going to be worth 25%, right, of your exam grade. So say this first problem out of 25 is worth 7 points, and if I were to go through it, and this is an example of someone, there's no name here, so, but if I was to just go through it, there's an equation of state of the system called internal energy for an adiabatic process, right? And so, okay, here they wrote for an adiabatic process. Okay, in one way, it's written, I think a little bit different in an adiabatic system, right? So I'm not going to take off for that because they're basically, it's reworded, but there's nothing wrong with saying it one way or the other, okay? So if you word it your own way, but you're correct, you're not going to get points off, right? So this is where the change in internal energy is equal to the work done on the system, right? For a system in thermal conductive environment, the heat flow or absorbed carb Q is given by, right? And then, so this is entirely right? And so I could go through others too, but whoever did this did a good job, and if I remember looking at it quickly, they got full credit. If not, maybe 24 to 25. I'll show you another one, right? And so we'll just look at the first two, okay? There is an equation in the system called the internal energy. The change in internal energy, delta E is equal to the work done on the system. Okay, that's not true, because it's only equal to the work done on the system when there's Q is equal to 0. Right? So right away, -1. So I guess I could just grade this right here, right? But, so -1, right? In a system in contact with its environment, -1. It's thermal contact, right? The energy transferred or absorbed is denoted as, okay, but then there's, okay, so there's a bunch of other stuff here, right? Right? And so denoted as, okay, I'm not going to get too picky on the word choice there, but denoted is not really kind of physics kind of thing, right? Or thermodynamics. It's not very engineering, right? But I'm not going to mark you off on it. But the first law does not indicate the direction a process takes during a natural reaction. Okay, so natural was here. That's fine. First law is a representation of conservation of energy. Okay, but then there was another one that they missed, right? Energy cannot be created or destroyed. Okay, well, whatever. So, okay, you might know that, but don't forget it on the exam because you're going to get a -1. There's nothing I can do but give you points off, right? If I start playing gray areas, potentially I get fired, right? Or if I do it long enough, right? I'm not going to jeopardize my job just for the sake of giving one person credit and then making a mistake and not giving the next person the same amount of credit. I have to be as fair as possible. Okay, so then let's go to the next one. So already if I rated this as 7 points, they got 4 out of 7, right? So I can just put 4 out of 7. There is an equation to say a system called entropy. Okay? The change in entry of an isolated system can be denoted as, okay? But this is -1 for sure because it's not Q reversible over T. It's the integral. You need a differential, right? This is just the non-conservative form of the differential, dq, right? So -1. But then it's denoted as, but this, one of the most important things here is where delta S, right, is greater than or equal to 0 for an isolated system. This is one of the most important things. So not only -1 here, but then he or she forgot to write that, so that's another. Right? And then, okay, that's fine to have this up here, but then one of the most important things about the second law is that for a reversible process, delta S equals 0 for an isolated system. Right? And so, okay, then, I'm pretty sure that's all that was right. And Okay, so then there was these comments, there was 4 of them. Entropy can be thought of as the number of options. Optimistic view. Entropy can thought of as the amount of disorder in the system. Pessimistic view. Okay, slightly different wording, but it's fine, right? The concept is fine. Okay, entropy indicates the direction of the natural process during a reaction. Okay, you need this, right? The entropy increases during a natural process. A natural process isn't me doing work, right? From a thermodynamics perspective. For me to do work on a system and decrease its entropy is not natural. So, for this natural process, entropy has to increase. Yes?
So that's an example, like for other processes, entropy could decrease?
Right. I can take a system, right, and I can decrease its entropy. But I have to do work on that to decrease its entropy. But if me and the system are isolated from the surroundings, so there's 2 parts to the system, me and the computer, okay? I can decrease the entropy of the computer, but my entropy is going to increase equal to or greater than. Only if I decrease the entropy of the computer and that process of me decreasing it is reversible, then my increase in entropy is equal to the decrease. You see? So they balance out to be 0 because we're isolated. So you can decrease the entropy of something. Or the entropy of something can decrease. But it's at the expense of something else. And for a natural process or a natural reaction, entropy is always going to, tend towards, an increase. Natural process. That's not me doing work on the computer. That's from the thermodynamics second law perspective, that's unnatural. The natural thing from a thermodynamic is for me to do nothing. Other question?
When I put this as an example on the quiz and the TA didn't dot me for it, but he scribbled it out, like he didn't.
Yeah, well, no, yeah, but I mean, I already granted, right? Okay. That's we'll have to talk with the TA about that,
okay.
But this is important.
Okay.
So on that note, if something's written there and the TA crosses out and says it doesn't matter, but it's written there, you should probably not trust what they say. Because, yeah, I mean, so, okay, if you forgot to do this, you got -1. Not much I can really do about it, given the TA misled you, but, okay, that happened. Okay, so then there was another bullet here, which basically says this is -1, right? And then which was this, but then I don't see anything here talking about omega. It'd be one thing if they put omega up here, but they didn't. Talking about omega representing the number of states of the system. So, another -1. So 1, 2, 3, 4, 5. They got 2 out of 7. What can I do? I mean, I can't do it any differently. I'd like to, if it was a little bit better, right? To give more. If it was a little bit better, I would like to give it more credit, right? But I can't. It's just not fair to somebody else who did it perfectly, or somebody else who just made one minor mistake and I'm taking -1 off of. For example, TA misled somebody and then they didn't put this part and they got 24 out of 25, right? Okay. So, and then, in a homogeneous process, that's just wrong, right? Right? It's a homogeneous system in complete internal equilibrium, right? So homogeneous, so that it's good we talk about, this on the third law here, the idea of homogeneous. So homogeneous is a block of copper with no defects. It has the same ordering of all copper atoms within. So if I remember right about, the structure of copper, I think it's base centered cubic, but anyway, so you have 1, 2, 3, 4, and then 1 in the middle, right? So you break it down, but you can break down copper and its atom orientation into a bunch of little tiny blocks, and then all the blocks are identical. So homogeneous system, an example, copper with no defects, right? No impurities, nothing, right? Just all copper atoms, all having the same spacing between each copper atom and angles between each copper atom, right? No defects. So in a homogeneous system is usually what we have, right? And so it's really hard to make homogeneous systems. You have to go, like space station, right? Where there's no gravity, or you have to do a bunch of things, right? Temperature has to be uniform. You can't have any temperature fluctuations during growth of a homogeneous system. Anyways, so -1 here, just had a little, divergent on what a homogeneous system is, in case, because you're writing it, you might as well understand what it is after the end of the course. So homogeneous process, whatever, not wrong, is wrong. So, and the entropy decreases as temperature approaches absolute zero. That is true. But entropy approaches absolute zero. The entropy approaches absolute zero as the temperature approaches absolute zero. So this is just the idea of decreases. That's worded, incorrectly enough that it's another -1, and then there was this stuff here, and 0, right? But okay, so entropy equals 0 implies this equals 0. But you need to put, you need to do kind of a proof type thing, like which implies S approaches 0 as T approaches 0. So 1, 2, 3, 4. This one, it's not graded as harsh as the second law. It's easier to get 7 out of 7, but okay. But so 3 out of 7, and then if two particles are in thermal equilibrium with third, they are all in thermal equilibrium with each other. Particles, I guess, is true, but really it's two systems from a thermodynamics, right? Because I could, in layman terms, I could say a particle is an electron, right? So I'd say -1 out of 4. So 3 out of 4. So I can add it all up, and 3, 6, 10, 12. 12 up to 25. So by the time the final, make sure you don't make silly mistakes, right? Because this person probably thought they knew the laws and they were going to get full credit on it, and then if you just look through, they ended up getting less than half credit. But for me to be consistent with every one of your peers, I have to do it this way. Question?
Speaking of the final, is it also the laws also worth 25%?
They're about 20%. It's usually 6 problems on the final. So. But I'm going to ask more questions on the laws on the second exam and things like that, and it ends up being a huge portion of your grade. Oh, just as another example, this is what somebody else put. No, you shouldn't laugh. You should. It's hard not to, but come on. How do you expect to survive as an engineer when you're doing this? I told you exactly what you needed to know. If you can't do what is told to you several times right, I don't know what to say, but granted, yeah, there might be personal problems and all this other stuff that takes place, but even that, you didn't have it the whole semester, and if you are having such situations the whole semester, you need to not be doing bad in class right now. You need to be focusing on that and maybe do other things, because you don't need to dig yourself 2 holes, right? So, if that's the case, you really need to go talk to somebody, right? And if the case is you think you're studying and this is what you produce, you need to go talk to somebody. Because you need to have conversations on how to approach things, so you can be a successful engineer later on. This is the tedious question form, right? Third law has nothing to do with entropy. But anyways, I don't even know what to say. 2 out of 25. That's generous. So, this is the whole superheated steam problem, and so I said, make sure in the future when you do the tests that you try to, don't even look at the options. Just look at the problem. And solve it like you're an engineer, right? Don't look at this. Just look at what the problem statement is and try to solve it. And so what is the step 1 of solving a problem? My opinion, but what you should do. Draw a cartoon, right? Second step. Well, boundary is part of the cartoon, but if right, do full energy balance. Write out the full energy. As soon as you draw your cartoon, you know whether it's a closed system or an open system. If you don't, you need to get better at writing cartoons, because how can you solve a problem? Right? Don't take. I'm going to record it. Please don't take pictures. So if you're drawing a cartoon of the system, and you can't draw a cartoon to identify whether it's an open or closed system, there's no sense doing full energy balance or anything else further. You don't understand the problem at a basic level enough that mathematics is just going to make it messier. You'll never be able to apply the right boundary conditions or solve the problem correctly. You might get lucky, but draw a cartoon. So as soon as you do that, you should be able to determine whether it's an open system. Of course, this turbine problem is an open system. And then I just, rearrange things around. And so, and then if I write it all out, right, it's an open system that's running at steady state. So the change in internal energy, and so just move this over here, and I already specified everything else. I'm just going to add for the sake of argument. So say if it looked like this, that would be right, but of course it just hasn't been simplified to put this to 0. Now really, with the energy balance form of the first law, we're doing it so there's all the forms of energy in, all the forms of energy out, and then all the forms of energy within our system. Typically you just say heat, what is the heat transfer, the rate of heat transfer, and then the rate of heat transfer, right, the total heat transfer is equal to Q in minus Q out. So I could just have Q trans equals Q dot in minus Q dot out. And then in this case, when Q dot trans is negative, okay, that implies that he is leaving the system. When Q dot trans is positive, that implies that the net heat is coming in. I could do the same with work, but anyways, get the idea. And I'm just going to point out that this is the right answer. What series of expressions are right for describing the input and output enthalpies? Now this is really important to talk about because we're talking about, right, from the turbine perspective, we have a control volume of steam, superheated steam coming in, crossing the turbine boundary, right? And so within that control volume of steam coming in, it has properties. It has a temperature and pressure. So, so H1 represents the enthalpy of the superheated steam coming in, right? And so this is true, right? And then I have this one here. This is the output in gas form. Okay, is that true? What is the output?
Doesn't it say that it comes out as steam still? Yeah. What does the question say?
Let's go back.
The output steam.
Saturated water.
Oh.
It's saturated water, but you can think of steam at 100 degrees, so it's not really steam.
Just on the steam.
It's saturated. It's on the bell curve, right? So if I plot a bell curve related to the problem, okay, I come in over here and I end right here. So whether I want to do temperature or pressure. So this is state 1 and this is state 2. This is, right, there's a corresponding temperature and pressure here. This is superheated steam. It comes in, right, and then you're somewhere within the bell curve. All this is saturated. So if the steam concentration was 100% of saturated, then you'd be right here. If it was 0%, you'd be over here. Okay, so back to these. Fluid, okay, so, and then here, saturated water. Well, it's not saturated water, it's steam. There's why you have to pay attention to steam and saturated water is because this is in a table. And if you grab a saturated water, and there might not be, if you look in a saturated water table, you're not going to get the properties for steam. You won't even find a temperature and pressure that's related to it. So this corresponds to where you look it up, right? It's the phase. So it comes in as superheated steam, right? And I can't look up in a table H at T1, P1, a saturated water table to get H1. You'll never find it. So this is not. And then here, saturated water, this is true, right? Saturated water, this is true. But this one's wrong. And then here, this is true, right? So now what's the problem with this one here? Again, steam. Yeah. And then again, steam. And so anyways, it ends up being D.
I have a question.
Yes?
What is the subscript D mean? Does that mean gas?
Yeah, that's gas phase.
So it's saturated.
It's saturated water. So you're inside the bell curve. But inside here you have liquid and vapor. But it's saturated water. So water boils at 100, it's saturated water. So water boils at 100 degrees, right? But if I take a cube of water and I start boiling and say everything is just a little cube and it has water in it, and it's at 1 atmosphere, and it's at 100 degrees. So at that point, it can be either all vapor or all liquid. If I pick a point in time, it might be 70% liquid and 30% vapor. But it's at that temperature pressure. So you have to distinguish between the phase. But it's still saturated water. I should say saturated H2O, right? Would be a better or a more, it would be a more valid way of describing the bell curve. Instead of saying saturated, they should say saturated, right? Whatever the molecular structure is. So if this was a bell curve for ethanol, then it would be, saturated ETOH, right?
So there's two.
Instead of saying water, because water is typically thought of as the liquid state.
So there's two phases in H2.
There's two phases in here.
There's both saturated water. There's not.
Well,
steam.
it's saturated H2O, which H2O can be in the liquid state or the vapor state.
So it couldn't be A. Could it be A?
Well, the problem is that this is not steam.
It's a mixture though.
It's a mixture though. Like it's part steam, part.
Steam only means superheated steam. You have no other state.
Oh, okay.
Yeah.
That makes sense.
Okay, so what expressions are correct for the efficiency of the turbine? It turns out none of them were correct. There's problems with all of them, but okay, this is an important one. This was questions like this are part of our reason why I want to go over the exam. So I asked the TA this question; he got it wrong too. So, but yeah, I mean, okay, that's fine. I mean, we're all learning. So, you know, maybe last week I would have got it wrong. Somebody would ask it to me. I don't know. Maybe there's a chance. But I think it's important that we go over this. So we had an expression, right, for the efficiency of the turbine. And so I'll just write out the full what it was based off. So it turned out that the efficiency was work dot out over Q dot out plus work dot out is a simplified way of looking at it. Okay? But I like writing it like this. I mean, I could write out the full expressions, but this is what it would simplify down to. So in this problem statement, you have gas coming out, and in that gas coming out, it has an energy. The only way for this to be true is if I said that the kinetic and potential energy of the gas leaving the turbine was 0. There's no energy. I used all of that energy.
But wouldn't that be the case if Q dot was 0?
No, because you can still. It's not for in terms of the turbine. Useful energy isn't the gas coming out. The turbine is providing shaft work out. Now, so if I draw a picture.
So because that word is overall instead of thermal,
Yeah.
that's what makes it false.
So if I draw a picture, I have something coming in, I have gas coming in, I have gas leaving, I have work dot out, and I have some Q dot loss. Okay? So there's energy associated with this. I'm converting the energy associated with this into shaft work. And in this case, I'm converting the energy associated with this into shaft work without any loss of heat to the surroundings. But there still is energy here.
How could there be energy there if that steam coming out is not heated?
It's
Because the steam's not at absolute 0.
It's not at absolute 0. It's not at 0 Kelvin.
The energy.
Okay.
I haven't designed a turbine that takes steam in and outputs H2O at absolute 0.
Okay, so the steam coming out, it just wouldn't. It'd be called something else, not.
No, it's the fluid out.
It's your energy.
But and later on we'll go over exergy and they talk about the dead state. But in order for this to be true, the rest of the problem statement would have to say that the output H2O is at absolute 0.
Where would the output H2O go in our energy balance?
Well, this is the same as always, right? Energy in minus energy out, right, equals.
So the whole.
Right, so if I just put this here for the energy balance, move it up a little, right? Energy in, energy out, this is equal to 0. So I have all the forms of energy in. I had no heat in, I had no work in. This is all the forms of energy out, right? And now this is 0. So the useful energy out is this.
But there's still the.
But there's still energy out associated with this.
Okay.
At absolute 0, all of this stuff would be 0. Then I would have a turbine that was 100% efficiency. So you can see right away, to make a turbine that is 100% efficient, good luck trying to get to absolute 0, right? Because we put in the energy required to cool atoms, right? Near sub-Kelvin stuff. You have a whole building devoted to just taking a cube, right? And getting, a gas of helium, right, down to absolute zero. A whole building of energy put in to get something to absolute zero. So, but a good question, not necessary for you guys to score well on the exam, unfortunately, but it's a good, so you learn about how hard it is to make something 100% efficient. Now, of course, there's always heat loss too.
Right.
So even if you got it to absolute zero and there was heat loss, you wouldn't have. Then you would have some energy out in the form of heat, and you still wouldn't be 100% efficient. I guess another way to look at it is this expression right here. The efficiency is E out useful divided by E in, all the forms of energy in. And then you can rewrite it in this form, and I use this form, and because this was equal to Q out minus work out, but it's not going to, that's not going to be true. This isn't equal to Q out minus work out when Q out is 0. I don't know how much I should, I just want to talk about, so this is the right answer, and if we solved it, you can see that. I just flipped these things around. Anyways, and then this one I want to talk about because this is again talking about the state, right? How you define a property of a system. So the heat capacity at constant pressure of oil is approximately equal to the heat capacity at one temperature plus the heat capacity. So it's the average value between two temperatures. So if I plot Cp as a function of T, it does something like this, and this is T1, and this is T2. Okay, and I'm just saying the Cp of oil is approximately, in this type of situation, is approximately the average value. This plus this divided by 2 gives me that. So this is a valid statement. And then the heat capacity of oil, this is definitely true, right? Okay, so that's good. And then the density of oil, okay, same thing, just replace the heat capacity at constant pressure with density. So the density is approximately equal to, and of course, as T1 and T2 approach each other, it's definitely true, right? As the limit of delta T approaches 0, this is, or I could take a limit here, as the limit of delta T approaches 0, this Cp, approaches that, right? Anyways, so same with rho, right? And then H2 oil, right? And so oil leaves in the fluid phase, so this is valid. And then here I have H1 oil in the gas phase. Oil doesn't come in as a gas. It is at T1, P1, but it's not a gas phase. And then H2, yes, this is true, but so the subscripts matter. And so it's only A and B. And then let's go to the water. It's very similar. Cp, heat capacity of, now I did, instead of saying water, I said just molecular, H2O. The heat capacity of H2O equals that of ice water plus that of saturated steam. That's not true. You have to be in the same phase. So in the previous one I had oil, but it was in the same phase. You can't do this. I can't take the heat capacity of a gas and add it to the heat capacity of, okay, let's just use real numbers just as an example, okay? And let's do a plot of the heat capacity of water as a function of temperature, okay? It does something like this, but as soon as I cross a certain temperature, and now I'm in a gas phase, say steam, it does something like that. And this is a log plot. So this is 1 and this is 0.1. So I can't take the average value and say I'm here because I changed phases. Ice water, so water at 0 degrees C, right? It's not really ice, it's just water at 0 degrees C. And then saturated, I can't take the average value between these 2 points here and here. So I can't say CP of that leaving is the, right, the average is approximately equal to this plus this divided by 2, which would give me something right there. Because this is a different phase. So in reality, the heat capacity of water, say ice water, is, you know, at constant pressure, it's 4.4 kilojoules per kilogram Kelvin. But the heat capacity of steam at, say, 300, right, Celsius is like 0.001 kilojoules per kilogram Kelvin. So I'm going from 4 to like a less than a 0.1 number. Okay. Same applies here. I can't take the density. It doesn't, you know, it does give me an average value, but it doesn't necessarily work. In this case, I have to, the heat capacity of water, or the density of water within some control volume, I would have to have the volume of this, right? So I'd have to multiply by a volume, and then the volume of this divided by the total volume for this to be true. So that it would have to be volume, I'd have to volume weight it. So, but anyways, I go from phases. If it was the same phase, it wouldn't matter. But, and then this is the only true one. Let's see. Does that make sense? So, closed piston cylinder system. The piston is adiabatically compressed. Before the piston can respond, it cools at constant value. Then the piston rapidly returns to equilibrium such that there is essentially no more heat loss. So there's very little heat loss in the process, and this is the right one. So I just want to point out that this is adiabatic. This is not, right? This is not adiabatic. And this one, I'm going to just leave a question for now. So, and I like this problem a lot because it's not until you go through the mathematics and try to solve, right, for the area, that you realize that this process, even though I can compress from equilibrium, so right here, remember, I'm at equilibrium, I can compress through an adiabatic process, okay? But here, it's no longer adiabatic. As soon as I destroyed the adiabatic boundary conditions, I cannot take an adiabatic process back to equilibrium. I lost energy. I lost energy. There's no way to get back to here with less energy than I had before. This cannot be an adiabatic process. Okay, so we'll get to that in a minute, but this is the right one, even if you don't consider that. It follows that. You know that you went back to equilibrium, right? So it went from 3 to 1, and heat was lost, so then it did this, and then we can always look at, okay, so then we can say, is work done on or by the system, right? And we can use the counterclockwise rule, so that's really nice, because you know right away, right, what the area is by following the path, so you should know just by using the clock rule what you expect for an answer. And then when you get to something that might seem a little bit, when I trick you, or well, I don't know how to say it, but I didn't want to trick you, but I have to get you guys to think about this stuff when I give you the solutions. Now, if I gave you this test without any practice exam problems, I mean, yeah, that would be completely unfair, right? But but you had all the problems to practice, right? You should have been able to solve for them. You had a whole semester so far. So anyway, so it's really work by, or it's really work on, but these work ons. So if I just look at this, V2, V1. So let's first get back to how I got this part. So the integral of work on is equal to minus P dV, right? Work by is equal to the integral of P dV. So you didn't have to do the integral and solve for all of it to get the right answer. But it would have been useful if you knew how to do that. So for an adiabatic process, okay, PV to gamma equals a constant. This is gamma. Adiabatic process, PV to gamma equals a constant. Ideal or non-ideal gas, okay? Doesn't matter. Adiabatic process follows this. Now, when it's an ideal gas, I have another relationship, right, for the ideal gas law. So ideal gas, I have PV, M, R gas, T, right? And I can put ones here. And then using these two, I can solve for K. I can solve for K. And this is basically K. This is K. Solving for K. Adiabatic process.
So what are the ends in some of the other ones?
Yeah, so
It's because it's a polytropic process.
because once I destroyed the adiabatic boundary condition, I can't take a adiabatic process back to equilibrium, but I can take a polytropic process back to equilibrium. And so that's what you would in that curve. And so here, this part here is polytropic. And a polytropic process, PV over N equals a constant. And of course, this constant is related to the other one, but right, so this is constant C2 with an ideal gas. But in this case, when you do the numbers, in this case, when you do the numbers, okay, I know work on should be positive, but if I just look at, so I have a volume, and this has to be, so gamma is like 1.4. So if gamma was 0, there'd be a different story. But anyway, so I have a larger number, or a smaller number minus a larger number to a minus power. So this ends up being a negative number. Okay? And this one here is a smaller negative number. So I end up getting a negative number for work on in this context. Yes?
Can you go back to the problem?
Okay.
For in like the last sentence, it said that it returns to equilibrium such that there is essentially no more heat loss.
Essentially.
What's the difference between that and adiabatic? If there's no heat loss.
There is heat loss. It's essentially very small, is all that it's saying. There is some. There's some energy loss, to the walls of the cylinder or something like that. There is, that's why I had to put the word essentially. because it can't be 0. It's just small. I should have probably worded it in saying almost negligible, right?
Well, if it says consider a closed piston cylinder system, shouldn't we like assume that?
But the closed has nothing to do with heat dissipation, right? Well, closed it has everything to do with heat dissipation. Has nothing to do with mass, right? Transport. But if I were to say this is adiabatic as another check, and I would say that n's are equal to gamma, right? Because if it's adiabatic, then n is equal to gamma here. Then I have the same number, right? Plus the same number. Or I have one number, minus, because this is a plus sign and I go from 1 to 3. But anyways, so it's really minus 3 to 1. But you get the idea. It says the work on is 0. If n equals gamma, so basically saying that from state 3 to state 1 is adiabatic, work on is equal to 0, but just looking here, I have area. Okay, so this is it's kind of a complicated problem, but the main point is, as soon as you take an adiabatic process to one state, the only way you can get back to equilibrium is if no energy, and an adiabatic process is if no energy was lost. So as soon as I break the adiabatic boundary conditions, I cannot take an adiabatic process back to equilibrium.